Yeah. So here, let's take a look at this sample problem. So here we have a disk, we have a charge disk. So the electric potential at any point on the central axis of the uniform charge disk is given by this expression. Actually, we derived it a few pages ago. I think here, yeah, here. This one. So, and then we can make use of the this expression to find the electric field by the electric potential. So starting with this expression, derive an expression for the electric field at any point on the axis of the disk. So yeah, so it is very simple because we just only need to take the derivative. Actually, you can just regard it as a v of z, which is a function of z. All the other values are constant. So actually, we need to find the E field in z direction, Ez in z direction, So actually, Ez is actually a negative partial derivative of v with respect to z, like this. So this is nothing but minus partial z and sigma over 2 epsilon naught times square root of the z square plus capital R square minus z. So we just put this expression here, and this term is a constant, so we just put them in the front, and then we take the derivative of these terms, which is not so difficult. So this is minus sigma over 2 epsilon naught, and then this is 1/2 power, actually, z square plus capital R square. Like the square root is actually z square plus capital R square, and then 1/2 power. So when we take the derivative, we just multiply it by the power, which is 1/2, and then the power minus 1, which is 1 over square root of a z square plus R square. And then don't forget the chain rule. We take the derivative of for the inner function, which is 2z plus 0. So we times 2z here, and then minus the derivative of z is 1, like this. So we can just simply cancel this 2 and this 2. And finally, we can come up with the expression like this is -1, this is negative. So we have sigma over 2 epsilon naught, and then we distribute the negative sign. So we have 1 minus z over square root of z square plus R square. So this is what we get. And this expression is actually the same as what we have derived in chapter 22. And if you still remember, actually, when we need to calculate this expression at the time, we need to separate this into many rings, and then find the dE in different direction, do the cancellation, and then do the integration. So it might be more difficult. And for this one, the first step we did is to find the electric field, electric potential generated by this disk. And this is easier than to calculate this E field, because the electric potential is only a scalar. So we don't need to do the vector decomposition, and then but still, of course, we still need the integration, but we don't need to bother the component of along different axes. And then after we find this electric field and then take the derivative. Take the derivative would be easy. In calculus class, you know, take the derivative will be easier than to calculate the integration. So that's the point we did it here. Okay, so the next we will introduce another variable called the electric potential energy. Electric potential energy. So it is of a system. The electric potential energy of a system of charged particles is equal to the work needed to assemble the system with the particle initially at rest and infinitely distant from each other. So at the very beginning, at the initial state, we put all the charge infinitely far away, which means there is no energy stored in that system. And then if we have a discrete charge, we try to pick one after one charge at one time and then one after another, and then to form the system we would like to concern, and then we try to see how much energy we need to put all the charge in that shape. And for two particles at separation r, U is actually this expression. So we still have this K here, and then we have Q1, Q2 over R. So we altogether have four expressions about the electrostatic force, known as the Coulomb's force, and also the electric field. Also, we learn the electric potential here. Also, here we have electric potential energy. So altogether, we have four expressions. And if we have multiple charges, then we need to calculate 2 by 2. We pick two of the n particle, and then we calculate their potential energy, and then we add them together. So this is like a summation, but every time we need to take two particles, I and j. Then, of course, we need to sum over I and j from 1 to capital N, and every time we pick two. So altogether, we will have NC2 terms, but N choose 2, which is when you learn the combination. So we know NC2, or some textbook, it will be written as bracket N2, something like that, which is actually N factorial times 2 factorial times N minus 2 factorial, which is nothing but N times N minus 1 over 2. So it is like, for example, if we have 3 particles, ij 1, 2, 3, 1, 2, 3, something like this. So 1 and 1 we don't need to count. So no here, no here, no here. So we need to count the potential energy between 1 and 2, 1, 2. So this is U1, 2, and then U2, 1 is actually the same. We don't repeatedly count it. The lower half triangle. So we also have U1, 3 and U2, 3. So here for N equals 3. We have 3 terms here. So it is like 3 times 2 over 2 equals 3, like this. If we have 4, we still have U1, 4, U2, 4, and U3, 4. So we altogether have 6 terms, which is like 4 times 3 over 2 equals 12 over 2 is 6. So here we have 6 terms like that. Okay, so let's see a simple example to see how it works. So here it says a 3-point charge held in fixed positions by force that are not shown. So what is the electric potential energy U of this system of charge assume that D equals 12 centimeters, and that Q1, Q2, Q3, and in which Q equals blah, blah, blah. Okay, so here we have three particles. So the total energy will be U12 plus U13 plus U23. So actually, potential energy is also a scalar, so that we don't need to bother the direction. We don't need to bother the direction. So it is K times U12 is actually Q1, Q2 over, in this question, D here. And then Q1, Q2. And then plus Q1, Q3 over D plus Q2, Q3 over D. Okay, so we can just factor D out. We have K over D multiplied by Q1, Q2 plus Q1, Q3 plus Q2, Q3. Okay, so we can just plug in the values. K is 8.99 times 10 to the 9th power. D is 12 centimeters, 0.12. And then Q1, Q2, Q1, Q2, Q3. Q1 is 1 times Q2 is -4. And then Q1 is 1 times 2 plus -4 times 2. And then don't forget to multiply the Q square, which is 150 times 10 to the -9th power quantity squared. Okay, so the answer will be -1.7 times 10 to -2 joule. Yeah. So this is actually a negative energy. And you can simply imagine that these two are positive, so there will be some charges repelling them, but here this is positive, this is negative. They are attracting each other. Which means spontaneously, actually, they tend to repelling each other. They tend to attracting each other, so that they will try to pull them together. But of course, you need some work to hold it there. But yeah. Okay, here we have another sample problem. So it is quite long, but actually that's not so difficult. So here it says an alpha particle, 2 proton and 2 neutron. So this is alpha particle, 2 proton, 2 neutron. Actually, it is a helium, which is the second element in the periodic table. So move into a stationary gold atoms. So this is gold with 79 proton and 118 neutron. So which is much larger, heavier, and has more charge, much more charge. So it has plus 79 E here. It is plus 2 E here. Oh, okay. Actually, we don't have electron for that one. So it is like 2 plus, something like that. Okay, so passing through the electron region that surround the gold nuclear like the shell and had it. Of course, the gold atom should have some energy outside it, but yeah, here we only concern the gold nucleus, so it only we only consider the proton and neutron here. So that surrounds the gold nuclear like a shell and had the direct the nucleus. So you try to shoot an alpha particle towards the gold nucleus. Of course, there are some initial velocity of this alpha particle, in this direction. And you can imagine that this is positive charge, this is another positive charge. So there will be Coulomb's force acting on them, repelling them apart, repelling from each other. So which means that there will be a force So there will be a force acting on this one, force, the Coulomb's force acting on it, which means that the velocity will become smaller as it is approaching the gold nucleus. So the particles go until momentary stop when it centers at a radial distance r equals 9.23 femtometer. Femto is 10 to the minus 15, if you still remember. Yeah, so this is r, and from the nuclear center. Then it moves back along its incoming path because the gold nucleus is much more massive than the particle. We can assume the gold nucleus does not move, so this is much heavier. And and what was the kinetic energy, Ki of the alpha particle when it was initially far away? So as much as it has kinetic energy, it do have some it has some velocity, then it will have kinetic energy. The kinetic energy is nothing but 1/2 m alpha vi square, Ki, the initial kinetic energy. So without considering the relativistic effect, actually we will learn the special relativity later in this semester. So what was the kinetic energy, Ki of the alpha particle when it was initially far away, hence external to the gold atom? Assume that the only force acting between the alpha particle and the gold nucleus is the electrostatic force or the Coulomb's force. So here we can consider the conservation of mechanical energy, which is the sum of the kinetic energy and also the potential energy. So as much as it is conserved, then we will have Kf, which is the final kinetic energy, plus the final potential energy. So this is I means infinitely far away, and then F is actually this point. I equals infinity far away. Okay, it's the final point. Okay, so here, actually Ki is what we know. Ki is actually what we want to find. I mean, what we want to find. So Ki, we just put Ki here, and if finally far away, the potential energy should be 0. So Ui should be 0 here, and for the final stage, here. So before it move away from the gold nucleus, then right at this moment, the Vf should be 0, because before that, Vf points to this side, becomes smaller and smaller, and then stop at this point and then go back. So right at this point, the Vf should be 0, which means that Kf should be 0. Kf should be 0. And we'll know that Uf here is actually the electric potential energy. So we have a Uf here. So Ki is like UF. UF is nothing but K times Q alpha Q gold over R. Okay, so this is nothing but 8.99 times 10 to the ninth power times 2 times 79 times 1.6 times 10 to minus 19 square over R is 9.23 times 10 to minus 15. Okay, so this is 3.94 times 10 to minus 12 joule. And actually, later in this semester, you will also learn another unit for the energy, which is known as EV. EV. How to calculate that? We can just divide 3.94 times 10 to minus 12 by 1.6 times 10 to minus 19, which is actually this number, So it becomes 24.6 mega EV. Mega is 10 to the 6th power. So you can also use this SI unit. Actually use this unit to describe the energy of a particle. Usually they use it like that because, as you can see here, if you use the joule, which is the standard SI unit for the energy, but there is a very, very small, it will be a very, very small number, 10 to minus 12, something like that. So they try to normalize it using the elementary charge. So actually one EV is like you use 1 volt of potential difference to accelerate a electron, to accelerate 1 electron. And then the energy at the electron will be 1 eV. So this is the physical meaning of the EV. Okay, so yeah, we have almost finished this chapter. So let's see. So potential of a charge, isolated conductor. So here you can see an excess charge placed on an isolated conductor will distribute itself on the surface of that conductor, so that all points of the conductor, whether on the surface or inside, come to same potential. This is true even if the conductor has an internal cavity, and even if that cavity contains a net charge. So you can see this graph. There is a car, and then a man is inside the car, and then you try to generate something like the thunder. I think it is artificial generated thunder hitting on this car, and the man didn't die. Okay, it wants to tell you that. So actually, the potential. This, of course, when you use the thunder to hit this one, maybe I can use yellow. Yellow. No yellow color here by default. Okay, let's see this. Okay, you use a thunder to hit it like this. Yeah, of course, the potential of the car will go up from the ground, But however, whether the man will die depends on how many power or how many current going through that guy. And actually, for the whole car, the potential will be kept to be the same because the shell of the car will be conductor. So actually, when the man sit there will definitely no or infinite or insufficient current going through that guy, and actually the current will something like going this way or the other way around. Yeah, actually this is electron, so actually the current will going from this way to that way. Yeah, the current should be go from the ground to this, like that. So actually there is no current going through that guy, so it will be safe for the man inside the car. So it is wise to enclose yourself in a cavity inside conducting shell where the electric field is guaranteed to be zero. Guaranteed to be zero. And a car, unless it is convertible or made with a plastic body, it's almost ideal. So in chapter 23, when you have learned the Gauss law, so it tells you that for conductor, then the charge will be at the surface, and the E field inside the conductor will be zero. So the man won't have any current going through him. It doesn't really matter whether the conductor is solid or hollow. Even there is some cavity inside the conductor, then the E field is still zero. So as you can see here, the voltage, or I mean the electric potential. The electric potential is like, so this is like a sphere shell. So this is our maybe our axis here. Our axis from the center to there, and this is 1 R equals 1 meter for this point. So if it has some excess charge distributed here, then the electric potential will be like, so this is inverse proportional to the distance, because you have learned that V will be K times Q over R. Yeah, like this. But inside the cavity, inside the conductor, the voltage or the potential or the electric potential will keep the same. So as much as you try to get the electric field from this one, you will need to take the derivative of it. Like this. So taking the derivative of this constant will be zero. So we have a zero E here. And then this is decreasing. This is like something like V equals a constant divided by Z. So if you take the derivative minus dV dr, it is like minus C times -1 over R square. So it will be C over R square. So you can see it like this. So this is proportional to 1 over R. This is proportional to 1 over R squared, like this. Or if it is the other way around, you can just integrating it from 0 to some R, then you will get delta V will be from will be like a negative the line integral E df from I to F. So suppose the potential at the center point is this value, and then you start to integrating 0. So it becomes 0. And then you further integrating these parts. but with a negative sign. So this is positive. Integrating this area will still be positive. For example, if you're integrating this part, which is for this point, for this point, then you have a negative sign here. So you keep decreasing like that. Okay, so this is nothing special. It just reiterate this E equals negative dVdr and the integration of the E field. So far, we have learned several variables: electric field, electric potential, potential energy, and also the Coulomb's force. So you may be quite confused. And here I summarize it like this graph. So in chapter 21, you have learned electrostatic force, which is like K times QQ0 over R squared, like that. And then in chapter 22, you learn the electric field like this. And then in chapter 24, you learn the potential energy and the electric potential here. So here we have all the three expressions. We have K in the front. We have K in the front, 1 over 4 pi epsilon naught. And then for electrostatic force, we have Q times Q0 over R squared. So for potential energy, we also have Q times Q0 over R rather than R squared. And for electric field, we have only Q. We don't consider the test charge. And then we have R squared here. So we have R squared, R squared. Here for electric potential, we only have Q over R. We don't consider the test charge. So we have Q, Q, R, R, and then Q0, QQ0 here, like that. So when we like to converting the electrostatic force to the electric field, we use this F equals Q not E to converting between them. This is a relation between the electrostatic force and also the electric field and the electric field. And likewise, for potential energy and electric potential, the relationship is like the potential energy equals the test charge multiplied by the electric potential. So horizontally, we only need to multiply Q0 or divide by Q0 if the other way around. Okay, but vertically, if you need to convert electrostatic force to potential energy, we definitely need the derivative, or generally the gradient, or the other way around, the line integral. So likewise, for the electric field, you have seen it before. When you need to convert the electric field to the electric potential or the vice versa, you need this line integral to convert the E field to the electric potential, or on the other way around, you need the negative gradient. Okay, so this is more or less like the electrostatics. Actually, electrostatic means you will only consider a single moment. You will more or less assume all the particles to be stationary at the moment you would like to calculate. Then you would like to find what is the force between them, what is the E field generated by that structure, and what is the electric potential generated by the structure. But actually, that structure might not be so stable, which means that maybe one second later, the system won't be like that anymore. But for some case, maybe for the parallel plate, something like that, then it can still be stationary. But under the electrostatics, there is an assumption that the particle doesn't move at all. at least at least at that moment. At least at that moment. Okay, let's see some additional example. We don't have additional example one because it is chosen in the uh, for the selected problem. So I don't do it here. So let's see this one. So a plastic wall has been bent into a circle of radius capital R equals 8.2 centimeter. It has a charge Q1 equals 1.2 picocoulomb, uniformly distributed along 1/4. 1/4. So this one, Q1. Yeah. And a charge Q2 equals -6 Q1 uniformly distributed along the rest of the circumference with V equals 0 at infinity. What is the electric potential at the center point of the circle? So we like to consider the potential at this point. Okay, so this is pretty easy. So VC equals K times Q1. Actually, Q1 has a distance, it's a equal distance to C because this is a circle. It is a circle. So that actually you don't necessarily need to integrating it. Integrating. So yeah, it makes life easier. So Q1 over R, it is pretty much okay. Even though you can still try to separate into many small segments. So you have the dq over R, but actually R is a constant. So integrating it for a different angle will still be integrating a constant. So we just skip this part. And likewise, for Q2, we have a Q2 over R here. So we can just plug in K times Q1 is 1.2 times 10 to minus 12 over let me just plug in 8.99 times 10 to the 9 power. And then R is 0.082 plus -6 Q1. So -6 times 1.2 times 10 to minus 12 all over 0.082. Okay, so yeah, so this is minus 2.3 volts. Yeah, because it is there's a net charge, there's a net negative charge here. So the voltage or the electric potential here will be negative. So for question B, rather than asking you for the point C, it asks you the electric potential at point P. So here, what we would like to find is this R, this R. Yeah, this R, this small R. So this small R is actually R square plus D square, and then take the square root by the Pythagorean theorem. So R is 0.082 square plus D is this one, 6.71, 0.0671 quantity square, and then take the square root. Equals 0.106 meter. 0.106 meter. Okay, so VP will be K times Q1 over small r plus Q2 over small r. So this is pretty much like 8.99 times 10 to the 9th power over r is 0.106. And then 1 minus 6 times 1.2 times 10 to the minus 12 power. So this is minus 1.78 volts. So for this one, if you really need to find the electric field at that point, it might be tedious because it is not symmetric at all. It is not symmetric at all. So finding the E field at this point will be tedious. Okay, so here we have another sample problem. So it says a plastic disc of radius r equals 64 centimeter is charged on one side with a uniform surface charge density sigma, and then 3 quadrants of the disc are removed. So with V equals 0 at infinity, what is the potential due to the remaining quadrant at the point P, which is on the central axis of the original disc at distance d from the original center? Okay, so for the whole disk, we already know the expression will be something like this for the whole disk. This is for the whole disk. So now we just remove 3 quadrants of it, and with only this part remained, which means that due to the symmetric, this part and this part will generate the same potential, and so as this part and this part. Okay, so if with only 1 quadrant remained, then the potential generated by this disk will be 1/4 to it. 1/4 to it. Okay, so this is the V. This is the V. So now, yeah. So it is nothing special. We just need to substitute the numbers here. So sigma is 7.73 times 10 to minus 15 over 2 times 8.85 times 10 to minus 12. And then multiply by square root of z. What is z? Z here is actually d in this problem. So this is 0.259 square plus capital R. Capital R is 64 centimeters, 0.64 square minus 0.64, like this. Oh, sorry, not 0.64. No, should be D, should be capital D, which is 0.259. This. Okay, so the answer will be 4.71 times 10 to the minus 5th power volt. Okay, so this is the end of this chapter.